at ISTerre, and I'm working together with Piero. And the topic of my PhD is to detect and characterize seismic signals from dense arrays of new instruments. And in this talk and also on the poster, I will try to characterize a little bit of urban dust data, and we use coherent-based array features. So the data we used was from an experiment in Grenoble. So yes, you can see the outline of the fiber here. It runs basically from Saint-Martin-d'Air to Échirolles and up to Fontaine, for those people who know Grenoble a little bit. And it's a 50-kilometer long dark fiber. And we recorded data for 11 days. And there are various noise sources in the data, mostly cars and trams, what you expect in a city. And then we have more than a terabyte of data, and we want to understand this data a little bit more in detail. Okay. Somehow my PowerPoint is a bit independent. Yes, so we calculated coherence matrices for these. So basically the coherence between all different channel pairs or stations, how they call them in DAS, which is basically similar to calculating cross correlations between all the channels. And for example, here's one of these matrices, which shows like between all the channels the coherence values. And we do this because we expect that if we have some signal in the data, for example, cars, then all the channels who will have this car signal or this tram signal in the data will have a higher coherence than channels which just record something independent. So what we did then is that we took all of these matrices, we computed for each 20-minute window, and we concatenated them in one big data structure, and then we wanted to find a pattern in this data. Because all the windows where there's a tram present, we expect that this tram will cause a significant pattern in the covariance matrix or the coherence matrix, and this we try to detect. And so we did a non-negative matrix factorization, which is similar to PCA, because I think most people are more familiar with PCA. Instead that we have the constraint that they have to be positive, which makes sense because our coherences lie between 0 and 1. And what we can see is that for this data set, for example, if we deconstruct it and use a rank of 10 to approximate it, then in a lot of these eigenvectors, we actually see some sources. So for example, here this corresponds to the tram signal, or this is a street up in Fontaine. And we can also see that with only 10 eigenvectors and weights, we can actually reconstruct our matrices pretty well, which is quite cool because these matrices have a dimension of almost 500,000 entries, but with only 10 weights, we can approximate the signal really well. And this can be then also used for clustering. So this is what we did. We did in hierarchical clustering to basically group time windows with similar characteristics, so similar noise sources that are active together. Yes, and here are some of my results. So for example, in the bottom plot, you can see which cluster each time window was assigned to, and there's really a structure in the data that is mostly to day and night variations, but also inside the day. So for example, here this cluster mainly occurs like this is Christmas and this is a Sunday, or we have some clusters which just occur in the very early morning, and this is also seen here. So for example, cluster 6 just happens during weekends and really in the early morning, while this cluster occurs during days and mainly, between daytime when it's really active. You can see here lots of trams passing, lots of car passing. Yes, so this was basically more a test to see if our methods can be applied to these huge data sets. But next, we want to look at real seismic signals and at some more dynamic system like glaciers and volcanoes. Yes, so if you have any question, please come by my poster. I'm happy to discuss.